So how does something like a solid dissolve in water? Well, there's competing interactions. So there are attractions between the solvent molecules, two water molecules. There's dispersion forces, dipole-dipole forces, and hydrogen bonding between these. They're very strongly attracted. For dissolving sodium chloride, table salt, there's a strong attraction between the sodium ion and the chloride ion. In order for the sodium chloride to dissolve and mix thoroughly with the water, we have to compensate for those lost attractions. Because for this to get in to the water, we have to separate the water molecules and we have to separate the sodium chloride ions. So we have forces of attraction between the solvent and the solute. In this case, it's that ion dipole force, which is quite strong. And so the sodium chloride does dissolve in the water. Not all ionic compounds are soluble, though. We had that list of solubility rules that we learned how to use. In calcium carbonate, you have calcium ions and carbonate ions, but the attractive forces between the calcium and the carbonate are stronger than the ion dipole forces between the ions and the water, and so it does not dissolve. Predicting when that happens is not a simple matter, and that's why we just use the rules that have been figured out empirically. Any questions? So I think of this, here's sodium chloride, and we've got the sodium ions and the chloride ions, and they're all tight with each other and they're all together. And then water comes and is trying to lure these guys away from each other. And so chlorine has a negative charge, it's a chloride ion, and so the positive ends of the water come around and they make chloride feel comfortable. And she's like, well, I guess I could go away from sodium for a little while, and I'll go away, and she's surrounded by the water molecules. And then here's sodium, and the water molecules turn their negative side to the sodium, and they lure sodium away from the chlorine. And so they make sodium feel comfortable away from the chloride, and so it will mix. Any questions? So when sodium chloride dissolves, the individual ions separate completely. They're surrounded by water, and they mix thoroughly. The top of the water is just as salty as the bottom. It's a uniform mixture, a homogeneous mixture, and solution is the special word for that. How much salt will dissolve in water? If you try that at home, use a very small amount of water. There's a lot of salt. You might, if you used a big bowl, you might use up all the salt in the house. So just use a little tiny bit if you want to try that. Solubility is defined as how much of the compound, usually we express that in grams, will dissolve in a certain amount of liquid. So a lot of times we'll use 100 grams of water. So for sodium chloride, you can dissolve 36 grams of it in 100 grams of water at 25 degrees Celsius. If you add more, if you put in 36.1 grams in 100 grams of water, what will happen to the extra 0.1 gram? It's just going to sit there. Because the solution is full. You can't get any more sodium and chloride ions into it. It's saturated. So a saturated solution, we've put all of the solute molecules in there that we can. No more will dissolve. Maximum amount. An unsaturated solution means that we have less than the maximum. So if you put a little more in, it would dissolve. Supersaturated holds more than the maximum amount of solute. Does that sound impossible? Got more faith in science. So a supersaturated solution, you can't form this just at room temperature. What you do is you create a saturated solution at an elevated temperature because most things are more soluble at high temperatures. So you take hot water and you dissolve the solute and you get a saturated solution, and then you allow it to cool very slowly, and you can kind of trick the ions into staying in solution. This reminds me of, the cartoon characters, and they run off the cliff, and they don't fall until they notice that they've run off the cliff, right? So as long as you don't point it out to them, they could just keep running on thin air. So that's what happens with the supersaturated solution. When you disturb it, all of a sudden it's like, oh, wait a minute, and psh, and you see the crystals come. It can also happen under circumstances such as high pressure. So if you put your soda can in the freezer to cool it off, and you get it out before it actually froze and burst, but you open it, sometimes reducing that pressure is enough, and it will suddenly freeze. That's a completely different thing. I misread. It's cool, but it's completely different. Okay. This one is talking about opening a can of soda just at whatever temperature. Carbon dioxide has a certain solubility in water. And a soda is supersaturated. It's stable in the container because there's pressure on it. When you release the pressure, then the carbon dioxide begins to come out of solution. So it was supersaturated under pressure. You release the pressure, and that's when all the bubbles start forming. So supersaturated solutions are unstable. This is a beaker with supersaturated sodium acetate. And it's just sitting there being a liquid. If you peeked at our alum crystal beakers day before yesterday, some of them didn't have any crystals in them. What I did, because they should have crystals, some of them had become supersaturated. The beakers were too clean and too smooth. I went and I took a stirring rod and I scratched the bottom of them, and then crystals began to form. Not as dramatically as these, but that's why everybody had crystals yesterday. So I've got a couple of cool videos here. This doesn't have any sound. That's supersaturated sodium acetate. Looks like water. Poke a stick in it, and crystals begin to form. It's like, oh, we're not supposed to be in solution. And they will continue to form on the already formed crystals. And isn't that neat? It's like, wow. It'll stop when it becomes a saturated solution. So it depends on how hot you heated it and what ratio you used. But you can actually get it so that if you make the solution right, it will seem to be all solid. It's kind of a wet, crunchy solid, but it doesn't seem to have any liquid in it. So let's see if I have this stupid computer. So let's look at this other one. This one's called Hot Ice, Fun with Sodium Acetate. Again, no sound. They look like pom-poms. You can see the temperature is 52 degrees. Because as it freezes, as it condenses out, it releases energy and it gets hot. So it looks like it's freezing, right? But it's getting hot. Hot ice. It's solid. So it's, it's a little wettish looking around the edges there, but it's fun stuff. So then I do all kinds of fun things with it. Building sandcastles. So it's a liquid. When it gets disturbed enough, it says, hey, you're running off a cliff, it becomes a solid. It precipitates.
It's like those videos where you like freeze a soda like just right and then you pour it in a cup and it turns to ice.
A little bit. A little bit. That's super cooling a liquid, cooling it below its freezing point. So it's a little hard to read, but that's ice, spelled with sodium acetate. So I'll put those up on the YouTube channel. We don't want to watch that one. So, any questions? Solubility rules that we've learned how to use, those give us a qualitative description. They say this will dissolve, this won't dissolve. It doesn't tell us how much. So some of them, like calcium carbonate, they don't dissolve because the force of attraction between the calcium and the carbonate is just too strong. Molecular solids can also be soluble in water. Table sugar, sucrose, is polar and it dissolves very well in water as well. But nonpolar things like lard, vegetable shortening, those are generally insoluble in water because the type of interactions are different than what's in the water. Electrolyte and non-electrolyte solutions. An electrolyte contains dissolved ions. Those are charged particles. The charged particles can carry electricity. So when you dissolve sodium chloride in water, you have individual charged ions. Sugar also dissolves in water, but it doesn't form any ions. So it will not conduct electricity. So a non-electrolyte solution will not conduct electricity. Electricity is the flow of electrons, and so you have to have something to carry those charges. Solubility. Usually, this is for solids, usually as the temperature increases, the solubility increases. So we can see at 10 degrees, potassium chlorate, not much will dissolve, maybe 5 grams in 100 grams. But if you get up to boiling water, now you can do almost 60 grams. So solubility increases. It doesn't increase for everything, though. There are some that go down. You see, sodium chloride is relatively level, unlike some of the rest of these that change so much. So another life application. Sugar is going to dissolve more easily in hot tea than in cold tea. So if you're going to make iced tea and you want sugar in it, put the sugar in before you ice it. It'll go much easier. So the solubility varies with temperature. A technique that we can use to purify a solid is called recrystallization. So when we got our crystals of alum, some of them were really cool looking, but they didn't look like super perfect or anything, right? You can recrystallize them and get them to be more pure. So what you do is you take a saturated solution of the solid and then you heat it up. You let it cool slowly. You do not want to have a supersaturated solution forming here. As it cools slowly, the solubility decreases and some of the solid will precipitate from solution. When that happens very slowly, the forces of attraction are maximized between the ions in the solid and they exclude impurities because the impurity doesn't fit. When it cools quickly and precipitates quickly, then it includes all of those impurities in it. So that's recrystallization. You can use recrystallization to make rock candy. If you try this at home, make sure to look up, maybe on YouTube or something, some instructions. Because if you don't do it right, it won't work. You have to have enough sugar in the water, but you can make big crystals of sugar by recrystallizing it.